I mentioned the difference of squares where there's no linear term based on the result that the not opposite, the outside and the inside of your FOIL just happened to cancel out because they were the same number, but they were just conjugates of each other. Sorry if that was a mouthful. This is a difference of squares, but it's not in factored form, and I'm telling you to put it into factored form. Well, you just kind of follow the pattern that we learned when we first learned difference of squares. We can go backwards. So it's just going to be x plus 2, x minus 2. And let's put the difference of squares up here. So following that pattern, that's what this turns into. Another quick example, we have 9x squared minus 1. This is a difference of squares. The square root of 9x squared, I know we haven't covered roots yet, that'll be next chapter, but I think you can handle this. This is 3x. So it's going to be 3x plus 1, 3x minus 1. That's a plus. If you're ever unsure, you can always FOIL it back out to see if you get to this. Let's talk about SOAP. Is actually just another mnemonic. We just did the difference of squares. Now we're going to do the difference of cubes. And the way that cubes work, we can also do the sum of cubes. That's where the SOAP comes in. So we have x cubed, roll with me on this, plus or minus y cubed. It works for sum of cubes and difference of cubes. We can factor this as, write this pattern out first. This is just something you're going to have memorized. This is going to be x. I'm going to put a space, y. Then we have x squared, space, x, y, space, y squared. Just going to have that memorized. This looks like the perfect square trinomial, but without that pesky 2 in the middle. And then here is just an x and a y. Where the SOAP comes in is what sign you use in these blanks that I left out. S, which is same. So whatever you started with, whether it was a plus or a minus, it's the same for this spot here. Spot here is O, which is opposite. Whatever it is, it's actually the opposite here now. This was definitely the first time I ever saw this symbol. The minus or plus symbol just means that whatever this is, you're going to do the opposite of it. That's why it's a minus on top of a plus. And then this space here is just, I'm not going to write it like that, it's just always positive. So just put a plus there. You can rest assured that this is completely factored. None of these are going to be able to be factored any further than that. What do I mean by completely factored? Yeah, this. And I want you to factor this. Okay, well, they have a common factor, so start there. You always start there when you're trying to factor something completely, is that if they all have common factors, factor them out first before you do any sort of reverse FOIL or whatever. Factor out the common factor first. So we got 5 as a common factor. 5, we divided out a 5, so that's going to be 4x squared minus 1. Now, we are left here with a difference of squares. It wasn't a difference of squares when we started, so we can't do difference of squares in this form here. It was secretly hiding, it just had an extra factor of 5 lurking, obscuring it. So now we're going to keep that 5 there. We've factored it out, but we can't do anything else with this, so we just kind of keep it off to the side. And then we break this down as a difference of squares. So 2x plus 1 2x minus 1. Another example, let's see if I can come up with one on my head real quick. I could try and put it into factored form straight from here, reverse FOIL, but it might not work. Just like this, I couldn't do difference of squares right away because it wasn't a difference of squares. This might not work. I don't know, and I kind of don't want to try that. There's a chance that a trinomial can't be factored into two binomials because, well, this can't work. There's no factors of 2 that add up to 2. So we'll cover those in the quadratics chapter. We're only worried about things that can be factored. But this could be factored, but maybe not in its current form. I don't know, and I don't want to have to try. This looks a little too gumbled for me. 84 is pretty big. They all have an x in them. Let's take out that x. Oh, and they're all even, so we can at least take out the 2. So 2x on the outside. We're left with x squared minus 11x plus 42. Now, we try to find factor pairs of 42 that add up to negative 11. So 6 and 7 are factors, is a factor pair of 42, but 6 and 7 add up to 13, not 11. But 3 and 14, that works. I did that in my head. If you're not comfortable doing that in your head, write it off to the outside. Like 6 and 7, I mean, obviously 1 and 42 is way too high for negative 11. 2 and 24, 2 and 21. No. Can't do 2 and 21 to 11. They're too far apart from each other. And then you just keep going to your calculator and try to find the factor pair that works. 14 and 3 works. Crap. This is what I get for trying to do problems in my head. These have to be negative. Okay. These still don't work for the same reason, though, because it's 14 and 3. Sorry about that. I'm not sorry. Well, I am, but whatever. This is a negative 11, so the 14 has to be negative. Negative 14 is an x plus 3. It could be even more complicated after you factor out all of the common factors, put it into this form. Then you have this. Factor the trinomial into two binomials. Out of nowhere, one of those binomials could be a difference of squares, so you'd have to deconstruct that even further. That's what it means to factor completely. After every step, check to see if they have any common factors, if they can be two binomials like this, and then see if there's any difference of squares. And I actually think that might be a good order to think about. Yeah, I think that's it. Do a bunch of these. Do a lot of these, because we're going to do this, but with more steps in a little bit. Stay tuned.